Okay, in this video I'm going to talk about deriving Menelaus theorem from the Ceva's theorem. So in the previous video I talked about like the other way around, deriving Ceva's theorem from Menelaus theorem, and here it's vice versa. So basically, as a reminder, we have two theorems that are kind of related to each other, that have statements that resemble each other. So in one case we have a criterion of when the segments connecting the vertices to some points on the opposite sides intersect at a single point. So this is the Ceva's theorem. And in another case we have a criterion when the 3 points on the sides of a triangle are lie on a single line, so they are collinear. So A, B, C, D, E, F. So this is the Menelaus theorem. And so the criterion here is that for the Ceva's case it's that BD over DC multiplied by CE over EA multiplied by AF over FB. This is equal to 1. And in the Menelaus case, the same, the product of the same ratio, so the same left-hand side, but it's equal to -1 instead of 1. So this is equal to -1. So so again, as a reminder, so I made separate videos where I proved both of these theorems, and the proofs were quite different. So for the Ceva's case, it involved areas of certain triangles, and in the Menelaus case it was using similar triangles. But so it turns out that we can derive one from the other. So in the previous video I showed how to derive the Ceva's theorem from the Menelaus theorem, and now I'm going to show you the other way around, how to derive the Menelaus theorem from the Ceva's theorem, and this is more difficult. So when we derived Ceva's from Menelaus, we wrote the Menelaus theorem for 2 triangles, and here we are going to write the Ceva's theorem for 6 triangles. So this is a more complicated case. Okay, so we are going to prove. So we are going to prove the Menelaus theorem now, and so notice that the criterion here is if and only if. So this equality is equal to, so this equality holds if and only if the points DEF are collinear. But we are going to prove only in one direction, only that if they're collinear, then this equality holds. The opposite direction, the converse statement, it's actually easily proven using the already proven statement, like direct statement. So the converse is proven using the original statement itself easily. So we don't need to use the Cevas for this. So yeah, so let's draw another picture. So we have this triangle, and we have this line. DEF. Now we are going to draw several more lines. So we connect B and E like this. We connect okay, so let's draw a little differently. So we connect now like this. And we connect like this. So we denote this point, so this is D. This was originally denoted. This is D, this is X. This is Y, and this is Z. So now we are going to write the Ceva's theorem, the Ceva's theorem for 6 triangles. So let me first write the list of these triangles in advance. So we have I will give the list of triangles and the intersection point of the Cevians. So the triangle ABE and the intersection point D. The triangle ACD and the intersection point F. The triangle BCF and the intersection point E. The triangle BDE and the intersection point C, and the triangle CEF and the intersection point B. So let me show it on the picture. So I'm going to use different colors. So first the large triangle, this ABE, so the first one in the list, ABE, and the point D is kind of obvious. I'm not going to fill it with any color. It's the largest triangle on the like in the picture. But then all the other I will highlight it with color. So ACD and the point at the intersection point F. So ACD So ACD, like this. So this triangle and so let me why is this point? So ACD and the intersection point F, so this point. And then so I highlighted this triangle in black. So then, oh, not this. So this I didn't highlight with any color. So I will denote it as an empty circle. So now ACD I highlighted with black. Now BCF. So BCF is this triangle. BCF and the intersection point E. So this I highlighted with red. Then BDE. Okay, I missed one triangle. Okay, let me, so I wrote only 5, but I need 6. So let me, okay, ADF. ADF, the intersection point C, and here is A. Yeah. And the last one is CEF and the intersection point B. Yeah. So BDE. So BDE is this triangle. And the intersection point is A. This. So the next one I will highlight in green. So it's ADF. ADF and the intersection point C. This, and then finally CEF. CEF and the intersection point B. Yeah. So now let's write the ratios. So for this, so ABE, so this large triangle and the intersection point D here in the center. So we have BX over XE. I will like ideally we need to write it with vectors. So over XE multiplied by EC over CA multiplied by AF over FB. This is equal to 1. So now the second one. So it's GB over BC multiplied by, yeah, there's not enough space to write all of them. Okay. Over BC multiplied by C CE over EA multiplied by AY over YD. Okay, the third one, let me write it in the same color now. So in the red now. So in the red one, BCF BT over DC multiplied by CZ over ZF multiplied by FA over AB is equal to 1, so the next one would be in blue. So we've read that Bx over xe multiplied by EF over FD multiplied by DC over CP is equal to 1. So the next one is green. So FE over ED multiplied by dy over YA multiplied by AB over BF is equal to 1, and finally the last one, yellow, so it's FD over DE multiplied by EA over AC multiplied by CZ over ZF is equal to 1, and that's it. So we have 6 equalities. So what we do now is we multiply all of them. So we have these 6 equalities. We multiply all of them, and that's what we get. So let's write this carefully. So Px over xe over ec over ca af over fb multiplied by it would be easier just to, without rewriting all of this, just to show it here. Just to save time. So I remove this equal 1 everywhere, and I just write that this is multiplication. So each one of them is multiplied by the next line. So all of this is multiplication. So when we multiply all of this, at the end we should get 1. So now we look what is cancelled. There should be a bunch of stuff that is cancelled. Yeah, okay, we need to invert some of them. So because, for example, bx and xe, so this is here, and for it to cancel we need to invert, because like if you write the inverse of this ratio, it would still be 1, so it shouldn't shouldn't matter for the original Ceva's theorem. So we need to write the inverse of this statement. Now EF of t dccp. Yeah, so now bx over xe, this cancels with this. So now what else do we need to invert? Okay, so notice that when we invert both, when we reverse kind of each vector in the numerator and denominator, we keep the sign, so we can safely replace here dy ya yd and ya is ay, like this. So now now this cancels with this. Right, so now yeah, and we need to invert the last equality. Yeah. Yeah, so now we see that this cancels with this. Right, so now everything that was involved, everything that involved x, y, and z now cancelled each other. So what remains is only a, b, c, d, e, f. So all the points that were present in the original statement. So now we have yeah. So now there are some stuff that still cancels. So AB in the numerator cancels with AB in the denominator. So for CB, okay, so we have BC here, so here we need to reverse both numerator and denominator. So we write that instead of BC we write, instead of CB we write BC, and in the denominator instead of DC we write CD. So now BC cancels with BC. Yeah, and C. Something is incorrect. Oh no, maybe, yeah. Okay, we have now CA and AC, so to cancel this, so we need to invert, okay. Okay, so we inverted both vectors in this ratio, and now we can cancel AC and AC here. Yeah, so now what remains is okay, so CE1 and 2, so CE so CE is squared in the numerator. So let's write all the remaining factors. Yes, so then we have AF and FA. So this would be the same as if we write squared and we put one minus. When we invert one vector, we can put minus to it. So then we have GB, okay, GB and BG. So again, this would be minus GB squared then we have FD and FD cancel each other. Then we have FE and EF, so for this we need to invert one of them. Right, EF, right, GE. Yes, so now EF and EF cancel each other. Now DE and DE cancel each other. So that's all for the numerator, and in the denominator what we have remaining so we have FB and BF, so this would be equal to minus FB squared. Then we have DC and CD, so this would be equal to minus dc squared here, of course, squared is inside. Squared. And finally we have EA and EA. So this would be EA squared. This is all equal to 1. So from this we conclude that minus cancel each other, minus cancel each other. That's what we have basically. Yeah, so because it's squared, like we can no longer care about which direction, so whether it's dB or BD, like it's all the same. So it would be so BD over DC multiplied by yeah, we can drop all the vectors now because it's squared anyway, so the sign doesn't, the sign is not captured here. So BD over DC multiplied by CE over EA. So this is all squared multiplied by AF over FB. So this is equal to 1, and now, so this is simply BD over DC, CE over EA, AF over FB squared is equal to 1, and this is almost what we need. So this product is exactly the product that we need here for the Menelaus theorem. And the problem is that we don't have the sign, that it's minus 1 and not 1. So basically we conclude from this that BD over DC CA over CA over EA multiplied by AF over FB. So this is equal either plus 1 or minus 1. There are two cases. We don't know which one. So we need minus 1 for the Menelaus theorem, and the sign. So basically we established that the absolute value is equal to 1, and the fact that it's minus 1 and not 1, this can be by considering all the possible cases of the line, how it passes through the sides of the triangle, that like we can account for all cases and see that, verify that in all cases the line passes like either one extension of the side and two sides, or all three extensions. That it cannot pass it cannot pass one side and two extensions on the side. yeah, so with this like I omit this proof, this part of the proof, and we are done for the Menelaus theorem.